Hey everybody, this is Mr. Bells. This is Precalc A section 3-2. We're going to work and talk a little bit more on exponential problems, get in some specifics on logistics, and go from there today. So hopefully this will go wonderfully well for you. We're going to start with this problem right here. So I got 300 bacteria, and it's growing, and it's doubling about every 15 minutes. We want to know when will the bacteria, when will that population hit 10,000 total bacteria? So what I want to look at is these two equations. So population at time t equaling 300 times 2 to the t over 15, and population at time t equaling 300 times 2 to the 4t. And my question is, which one of those things do you think is a better situation? So first off, we're going to check the beginning parts, the 300s. So is that where the initial population should go in one of these exponential growth problems? That's what it starts with. That's what goes in there. We're looking pretty good on that. This says that it doubles. That should be the growth rate, so that's at 2, and those are in both those places. But notice here I put t over 15, and here I put 4t. And I'm like, oh, well, it says 15 minutes, so it means this one should be right? Well, this one says 4t. Why would it do that? So the answer should be that technically both of these things are right. You're like, wait, what do you mean both of those things are right? So I'm going to give you about 10 seconds to think about it and go, why might both of those things be right? Because they're definitely two different equations. Jeopardy theme song music coming in. So bad Jeopardy theme music. But hopefully you processed out that this one, this t, is minutes, and this t over here is in hours. Good deal? So if I think about this, if I knew my t was 30 minutes, then I could plug it into here. 30 divided by 15 is 2, right? And I have an exponent of 2. Here, 30 minutes is a half of an hour, so 4 times 1/2 is also 2. Good deal. So depending on what the units are, I can use both of these equations differently. And just because the original problem was given in minutes doesn't mean that I have to write the equation in terms of minutes either. I just need to make sure that I write equations that match based on the ones that I'm going to use. Okay, so if I had 6 hours, I can easily use this problem, and that's 24 sets of 15 minutes. Or if I had 6 hours, I can do 6 times 60, which is 360. 360 divided by 15, you're going to get that 24 also there. Good deal? Okay, so moving on, because I don't really care about the answers to that one. The 10,000, you guys can do that to solve either one of these things, and you'll see that it will work out for it. What I'm going to do down here is look at a logistic modeling problem. So we have this formula, c over 1 plus ab to the x. And that's the generic model that we're going to use. And I'm going to give you 3 bits of information. So A, B, and C. Those are our 3 bits of information. I probably should have used 1, 2, and 3, or D, E, and F, whatever it is. This C, this A, and this B have nothing to do with those 3 things, just to be clear on it. These are going to come from different spots. So IV says initial value. So what does that mean on a graph? So on a graph, if I have a logistic modeling function just like this, the initial value is that point right there. That's the y-intercept. The limit to growth, that's the max. Right up here, that's going to be 48. And a point on it is going to be 3, 15. And if I have those 3 things, then I should be able to find an equation that works out. So it's going to go through this point, connect through 315, and also max out right up there. Okay, so let's try and see if I can do this. Well, the process for this is something called using the taxi. And taxis are cabs. So what we're going to do is we're going to try and find the C first, which is this one. And then once we do that, we're going to try and find the A, which is this one, and then we're going to try and find the b. And if we do it in those orders, it should work out okay for us. Okay, so the c should be pretty easy. The c, the top number, is our limit to growth. So if I have this equation, or this set of information, I have this equation, I know that my c is 48. Look at that, that's already done. I know my numerator. So if I write this over here, I got 48 in the top. I know it's 1 plus. I just got to find my a and my b, and I know it's raised to the x power. Okay, so I did my c, and I can cross that off. Now I'm going to find my a. My a is this number right here, and you're like, well, how the heck can I find the a? Well, this initial value of 10 right here means, okay, if I'm trying to find the a, here's my process, means that if I use this, right, 0, 10, that's my y-intercept, my initial value. If I use this in my equation, I might be able to solve for some stuff. So I'm going to do a little substitution right over here, substitution. So I now know that 48 is equal to 1 plus a times b to the 0 power. Yes? And that has to equal 10. Plug in 0 in for the x and 10 in for the value of the function f of x. Not into the x in replace of f of x. So now I got this. Well, what is anything to the 0 power? Well, most of you know that that's 1, right? So I can just cross that off. That being 1 times a is just a. So I have this equation, 10 equals 48 over 1 plus a. Well, I simply, I've got to get the a out of the denominator spot, so I'm going to move that up here and divide by 10. Move that down there, so I end up with 1 plus a equals 48 over 10. Subtract the 1, and I get a is equal to 3.8. Because 48 over 10, again, is 4.8, minus 1, minus 1, 4.8 minus 1 is 3.8. And now I've got that value, so I got a equals 3.8. Yay, we did that. So I can come over here, and now I know that it's 3.8 times b to the x power. Again, this is going to be my function that's going to model this stuff. So far, so good? So again, you can pause the video at any time and re-look at any of this stuff, or you can rewind it to help you understand it. This 100% is going to be on the test. It will be on the calculator test. A lot of the understanding of this process could be on the non-calc, but this specific type of process is going to be on the calculator. Okay, so now let's go from here. I've done the C, I've done the A. Remember, we're taking a taxi. A taxi is a cab. Now I just have to find the B. So, well, the B is going to use the 3, 15. So to be able to find the B, I need to use the 3, 15. Well, you can see I've got a bunch of stuff over here. Where does the 3 and the 15 go into play? Well, I'm going to substitute the 15 in for f of x. So my equation is 15 equals 48 over 1 plus 3.8 b to the x, which in this case is to the 3rd power, because that's my x value. Now I just have to solve this equation for b. Sweet. So just like on the last problem, I'm going to take this part and I'm going to take this part. I'm going to change their places. So I get 1 plus 3.8 b to the x equals 48 over 15. I'm sorry, b to the 3rd. I did substitute that in. That's right there. So then how do I get this? Well, this is going to be a number. I can put that into my calculator. I'm going to bring this down for you guys right now. Okay, so 48 divided by 15, enter. I get 3.2, right? And then I'm going to subtract 1. Subtract 1 from both sides, so minus 1, enter, 2.2. Divide by 3.8. Divide by 3.8, enter. And now I have this, but I have b cubed is equal to that number. So how do I get rid of a cube? Well, hopefully you go, well, I cube root it. the cube root, whatever that number was on my calculator, and you can see it's, oh, no, you can't see it. Sorry, there's a glare. I just looked at my screen. 0.5789, so I need to cube root that. And you guys know that cube rooting is the same thing as raising it to the parentheses 1/3 power, right? Hopefully we've done this enough in the class. You're like, yeah. So there's my b. Now, can I just call that 0.83? No. We really want to store that as much as we possibly can. So I'm going to store that, and now I'm going to actually use b, alpha, and the apps sign right there, stored in b. Good deal. And I'm actually going to go backwards again, and I'm going to even store 48. I'm going to store that in C, enter. And my A a little while ago was 3.8, so 3.8. I'm going to store that in A, alpha A, just like that. So now I've got all three of those things stored. I'll kind of write it down over here now again. I believe my equation is 48 over 1 plus 3.8 raised to the 0.83345 raised to the x. That's what my function is. Okay, so I'm going to try and go ahead and graph that. So go to your, sorry, that's on the bad screen. So go to your y equals, and we're going to do C, 48, right? Divided by parentheses 1 plus 3.8 parentheses 0.83345. There's more stuff to it, correct? Parentheses raised to the x, and then close parentheses, that's my denominator. Yeah? Okay, now I'm going to hit zoom 6, and you can see that it looks like it's growing, but does it taper actually off? Well, again, there's a lot to this problem. So the first thing I'm going to do is I'm going to go to my window. I'm going to y max out at 60. Remember, I believe the limit to growth is 48. Let's see. Looks like it's still growing up, but it looks like it's starting to taper off. I need to go further to the right. So I'm going to x max out at 30 right now. Check this sucker out again. And you can see that it definitely starts to taper off over here. Let's do a quick little double check. 48 is my max, what I believe, and I hit graph. And yes, indeed, it definitely does get closer and closer to that line. Sweet. So if I know that the limit to growth is good, but that was the easy one. That was this, right? That was done as soon as I put this stuff in here. Now the question is 0, 10 on my graph? Well, I go to my table setup. I started at 0, and I look at my table. Is 0, 10 on my graph? And you're like, yes. And then I go, is 315 on my graph? I'm like, yes. Everything looks like it works. Sweet. I'm also going to do this. I do not have to do this, but I think it's good practice for you guys. Sorry. So I'm going to go to stat, edit, and I have extra data in here. So second plus number 4, clear all lists. I'm going to get rid of that data. Stat, edit. I'm going to go ahead and put those 2 points in just so you can see them on my graph. So 0, 10 was a point and 315 was a point. Good deal. I go to my stat plot, second y equals. I turn plot number 1 on. I have a scatter plot L1, L2, and I hit my graph. And now you can see that not only on the table was it there, but the 2 points that I said should exist do actually exist on my graph. Yay. Okay, now, you're like, Mr. Bells, a long time ago, you put and stored all those things as C and A and B, but yet you never used them. Well, I just want to make sure that you know that that equation came from those things, but look what I could do. I can do alpha C, right, divided by parentheses 1 plus alpha A, alpha B, raised to the x, close parentheses, just like that. And watch what happens when I hit graph. You can see my blue line turns to a black line. They are the exact same things. Now granted, there was a smidgy rounding going on right here. So if I look at my table, you can see that I got 10 and I got 10, right? And I got 22.283. I got 22.283. You're like, there's no difference between them, right? In fact, let's do this. Let's get rid of this one, just so it's not there. And let me show them side by side. So they look identical as we go down. Is there anything you see differently? I don't really see it, but let's go to this one, 25.468. So when I read this all the way off, my last digit is a 9. When I go to the right, you can see the last digit is not a 9 anymore. So there is a subtle difference. That's why we want to make sure these things go all the way. Now, watch what happens when I do this. Let's say that I just made this original equation 0.83 and I rounded that much. Now when I go to my tables, you can see, like at 4, I got 16.94 and 17.122. I'm going to say these are getting kind of maybe too much. So be very careful with your rounding. Now if I rounded even more and deleted that and just made it, well, let's say 0.8 was close enough. Now you can see on the tables, my things are definitely different. I do not want that. Look at that. In fact, when I go out here, I have some of these that differ by, almost 3. Don't round your stuff. Cool. So hopefully that was beneficial, helpful. Again, make sure you know this process. Okay, here, do the next one. I've got the half-life of the substance is 3 weeks. The initial value is 10,000 grams. It is now at 320 grams. How much time has gone by? So we're going to talk about definite examples that we're going to use some things on. So hopefully you could write that in an equation form. So 320 equals 10,000. Half-life means that the rate is 1/2 or 0.5, right? And it says 3 weeks. So we're going to go weeks divided by 3, and that we use that as an exponent. Awesome. So I'm going to solve this equation for weeks, and I'm going to go ahead and do this on my graphing calculator. So I'm going to go y equals clear. If you want to, you could just leave this, like store that in there. You know what I'm saying? Just leave that. Just hit enter on your equal sign, and it's just there for whenever you need it. You can turn it back on again if you're going to store stuff in C, A, and B, and you don't have to retype it if you want to. If not, just clear it out, ignore it, whatever. I'm going to go up here to my plot. I'm going to turn that off by hitting enter once so that those dots don't show up on my screen, and I'm like, what the heck is that from? So 320, yeah, I like that. 10,000, yes. Parentheses, 1 divided by 2, close parentheses. Raised to the, I'm going to do parentheses. I got to do x because it doesn't know w, divided by 3. Good. Now, before I do anything with this, okay, I want you guys to go, I'm going to try and get the answer without technology, or get close. So, here we go. 10,000 cut in half once, that's 5,000, right? In fact, that's 5,000. Then I cut that in half, that's 2,500. I want it to be 320, right? 2,500. Cut that in half and I get 1,250. Cut that in half, I get 625. I cut that in half and I'm at about 312 and a half. I want it to be 320. So it looks like it's not quite a full one, but it's really close to a full one of these. So 1, 2, 3, 4, and a partial. Is that my answer? No, because it says that this happens every 3 weeks. So it's really 3, 6, 9, 12, right? And almost a full another set of 3 weeks. So my guesstimate on this is probably around 14.9. That's my guess. Check it out. Use some stuff on our calculator here. 14.9, that's my guess. That's my guess. Okay, window. Because I got to make the graph work. I just said I believe it's around 14.9, so negative 10 to 30, totally good with that. I want it to equal 320, but I know I started out at 10,000. So I'm going to put it, I'm going to put it at 1,000. I'll show you the other in just a minute, but here we go, graph. There's my exponential decay, my half-life, again, saying that it's going to be half of whatever was there originally every 3 weeks. Second trace, number 5, enter, enter, enter. Look at that, 14.8973. My guess was 14.9. I'm feeling pretty good about my logic. I'm hoping you feel really good about the fact that you understood what I was saying during all of that stuff. Sweet. Okay, so moving on. Again, so just an example problem so that we talk about decay situation or half-life. What happens if it happens every 3 weeks? We can just go ahead and do that. W divided by 3. So now we're going to go here. I have a new equation, and this equation is, as you can see, obviously a logistic modeling equation. And it says I start with 1200, and I divide by 1 plus 8 times e to the negative 0.3t. And it's supposed to be about the number of ill students. How unfortunately ironic that situation is in our dealings with COVID right now. This again is February 18th, 2021 is when this video was made, in the middle of this pandemic. I'm hoping if you're listening to this in like say 2025, you're like, oh yeah, I remember that way back then, that all the crazy stuff that was going on. So glad that it's not any situation anymore. Cross our fingers. Okay, so what we're going to try and do is we're going to see what we can do with this. This says P, or P of T, is the number of students that are ill, that are sick. T is equal to the number of days. So what I'm going to try and do is I'm going to try and see if I can learn some stuff about this. So let's go right here to our graphing calculator. Go to our y equals, clear and clear. And I'm going to go ahead and type this sucker in. So I got 1200 divided by parentheses. I got to remember that every time. 1 plus 8e to the negative 0.3x close parentheses. So that's what my entry into this thing looks like. Remember, on the older calculators, you might need to put parentheses around your negative 0.3x. But this is what it has to be. Don't put it around 8e, because then it will raise the 8 and the e to that expression. I do not want that. So I'm going to go ahead and hit zoom 6. And I think to myself, man, that looks dumb. It's just way over there in that corner. And then I go logic, Mr. Bells, logic. This says, according to this, the numerator is the limit to its growth. So that's 1200. Well, my calculator only goes to 10 right now. That doesn't make no sense at all. So on my window, I'm going to have a y max out here at 1500. And now I'm going to hit graph and be like, ooh, that at least looks a little bit more like it. But you can see I need to go way further to the right. I'm even going to go down a little bit so you can see that. So on my window, I'm going to go down on my y min to negative 300. I've discussed this several times in class before, but sometimes in order to see that on my graph, I like to go about 20% below the x-axis. So 20% of 1500 is 300. Good. And this one, I'm going to go out here to 40. And now it's like, dang, that looks really nice. I can understand this. So the first thing I'm going to do is I'm going to hit trace and be like, oh, what does that mean? That means out of the 1,200 students, right, 1,200 students in this school, wherever this is, this place, this location, of those 1,200 students, after 15 days, 1,102 of them are going to be sick. Ugh. That is a nasty bug. That's much worse than COVID, right? But we're doing a lot of things to prevent this type of growth. If I go down here and I just randomly stop, that means after about 4 days, there should be 353 people that are sick. Again, this is if everybody's still just hanging out in one big party going on, and there's no contact tracing, there's no mask, there's no nothing. That the spread of whatever this thing was, that's what it looks like. Okay? So let's take a couple things. We're going to go here to the table setup, and we're going to start it at 0 days and look here. And you can see that 133.3 is the y-intercept. Well, where does that come from the equation? Well, I plug 0 into t, then 0 times negative 0.3 is 0. Anything to the 0 power is 1, so e to the 0 becomes 1. 1 times 8 is 8. So watch on my calculator, home screen, 1200 divided by 9. There's my 133.3, which is my y-intercept. Sweet. So maybe I extend this question and I ask, well, what about after 8 days? 8 days, how many people are sick? Could you use your table and your graph to be able to figure out 8 days? Like, yes. Or maybe I want to know if there's 800 people sick, how far into this this illness are we, right? And it's this modeling that goes on. Now, you guys have been up front for this completely, right? You can take a whole bunch of great data, you can take a whole bunch of history of this stuff, and you can try and make models. And if you guys remember when COVID first came out, the models said that without doing a bunch of restrictions, there was a chance, and depending on which one you look like, that there could be this many fatalities, or maybe looking at somebody else's statistics, there were this many fatalities. And then they said, well, no, it's not going to travel that far. Maybe there's only going to be this many. Or, you know, maybe it's going to be up here. And there's a lot of variables that go into play. Now, what I hope for you guys every single time is that what goes inside your, right? What goes inside your head is enough logic and common sense and search for truth, because that's, I'm going to say that's, you're not always going to get that right now in these times. There's too many things that come into play on this, that sometimes people have agendas, that they want the data, the statistics, to show one thing for one reason or another. Maybe they don't want it to look like this, right? They don't want it to look like this. And they're going to skew their data, they're going to skew their statistics, they're going to look at certain reports and they're going to try and say, I don't like that, that looks scary. And there's other people that would be like, man, I really want to show that. And it's your job. You guys are, some of the brightest that we have around making it into this class. It's your job to be able to understand the information that you're getting and make good decisions from it. I don't care which way you go with it. I just want you to be educated on that. Okay, so that's what that is. And you should be able to answer either one of those. It's just given an x, find a y, given a y, find an x, use your graphs, any of those things. So we're going to finish off with a logistic data model. So in order to be able to have a data model, we need some data. So it just happens to be right here, and we're going to do this one in class too. So you can skip this if you were in class and you know what the heck's going on. We're going to take some data. So this is from year 1900, 1910, 1920, 1930, 1940, all the way to the year 2000. This is the population of Florida in millions of people, right? There wasn't just half a person in 1900s, pair of legs just walking around going, what do I do? Of course, they couldn't even talk, right? Okay. In millions. So how do I go ahead and put that into my calculator? So first thing I'm going to do is I'm going to go here, I'm going to go stats, I'm going to go edit, I'm going to put that data in. Now if I put that data in and I do 1900 and I do 1910 and I do all of these things with these really big numbers, remember the x value is going to be your exponent. That x value is going to be your exponent. So let's go back for just a second, and let's say I did 2 parentheses 4.6 parentheses raised to that, and my x was 1910. Watch what would happen on my calculator when I did that. Overflow. Overflow means that that exponent is way too high. Way too high. I can't do that. I can't go that big. That means it's more than 99 decimal places for the thing. So how do I deal with this on my calculator? What I have to do is, if I'm doing dates all the time, what I'll do is I'll start with my first date as times 0, and then 1910 would be 10 years later, 20 years later, 30, 40, 50, 60, 70, 80, 90, and 100 years later. And I know that hasn't been many times where we've actually gone through and had more than 2 or 3 data values. But like in a stats class, I might have 400 different data values representing some things that I want to look at all that statistical data. Typically, we would just transfer that data, and we can do that through the little cords that we have on these things, or even on the older calculators. There's little plugs that go back and forth that can transfer data. Okay, so over here, I got to put this in. So in millions, 0.5, 0.8, 1, 1.5, 1.9, 2.8, 5, 6.8, and 9.7, and 12.9, and 16. Good? Now, if you were watching carefully, yes, I did that on purpose. Okay? Just a little while ago, I knew my data was 6.8, and I typed in 5.8. My point is, it's really important. You guys could know how to do all your tech stuff on here, but if you do data misentry, it's going to throw off your equation, and we don't want to do that. So take a few extra seconds whenever you're sticking data into your calculator and double check to make sure that all of your numbers all the way through here are exactly what this data is. Okay, so I'm going to change that 6.8. Hopefully that clues you in. You're like, boom, that makes sense. I can do that. Awesome. So I'm going to go ahead and I'm going to look at my stat plot. I'm going to go ahead and turn my stat plot on. And I want you to see that this data actually does look like it models a logistical model. Okay? So before I do this, I'm going to hit graph. I'm like, yay, does that look good? Now, of course, that's an old equation. That has nothing to do with what we're doing right now. My window's not even set up for this data. Right? My x's go from 0 years to 100 years. So I'm going to go from -10 to 110. My y's actually go from 0.5 to 16. How dumb does that look with those things? So I'm going to go from -5 to 25. And you're like, Mr. Pels, how could the population of Florida be 25 people? That doesn't make any sense. So reminder again, this is population in millions of people. And this was the year 2000. Maybe it's even bigger now. I guess we'll find out. Okay, so now I'm going to go ahead and hit graph and look at that. It kind of looks like it's exponential growth. But right about in there, that upswing kind of starts to taper off. Well, we want to be able to find an equation. Now, could we use our CAB situation that we had before? Well, we can't really do that because we don't know what the limit to growth is. We don't know what Florida's population is going to max out on. So I could use my initial population of 0 and 0.5. I could use any of these random points to be a random point. But since I don't know my maximum sustainable population or limit to growth, whichever way you want to refer to it, I got to let the calculator do it for me. So if I go stat and I go calc, I look down here and I go, is it a line? Definitely not a line. It's not a parabola. It's not a cubic, not a chordic. It's none of those things. It's a logistic. That's what I need. Now, I will tell you there's a lot of computation that goes into play with this. So when I hit enter to do a logistic, unlike a line, which pops up in like less than a second, a logistic, when I go through here and do this, vars, y vars, function y1, it might take a little bit longer to process all of this data. Now, this is the top of the line TI-84 plus CE for what's going on right now. So when I hit enter, it'll be a little bit faster than some, but you can see it's thinking, it's thinking, it's thinking, it's still thinking. Poof, there's my answer. On an older calculator, it might be 5 or 6 times that long. Cool, so this is what it says. It says the C is 28. So according to that, Florida's population shouldn't get any bigger than 28 million based on this prediction. Well, if I was Florida, I'd have a decent idea like, whoa, here's how I want to build my cities. Here's what I want to be able to go for infrastructure. Here's what I should be able to expect. How many hospitals across the state? How are my cities growing? All of those things that population modeling can help us understand. 81.9 is your A. That's right in there. E means that that's continuous change going on. And 0.047 for my B. Sweet. Everybody good? But look, hit graph, and look at how good that models it. Now, there wasn't an R value on this, right? There was no correlation coefficient. That's because the equation is just too big for us to be able to model it with Logistic. But if you look at this line, this curve going through here, I'd say my R value is pretty flippin' nice. Cool. I'm going to go to my window now. I'm going to go to X max. I'm going to go out to, I don't know, like 200. And when I do that, you can see that it definitely shows, oh, it goes higher than what I have there, window. Let's go up to 30 million people. And that's kind of what it looks like. I feel pretty good about that. So I'm like, hey, what's the population supposed to be right now? Let's use this as a predictor. So I start my table set up at 2021. That's the year 2021. Good? You guys feel good about that? Yes? No? Give you time to think. You can pause the video right now. What you thinking? So hopefully you said no, Mr. Bells. That's bad. That's bad. Those aren't my X values. Look at stat, edit. These were my X values. The year 1900 was 0. So when I go back to my table setup, what is the year 2021? It's 121, because remember the year 2000 over here was 100. So 2010 would be 110, 2020 would be 120, 2021, there we go. I look at this, and that says the population of Florida should be about 21.94 million in 2021. This is what I do. Hey, Google, right? Siri, Alexa, I don't know where you're watching this video. Ask them, what's the population of Florida right now based on the latest census data? And it might be from 2020, so maybe we have to go there, but it should be pretty close. I'm feeling pretty good about it. Okay, so hopefully a lot of that stuff just made sense. That was the last example problem that we're going to do from this. Study, do your homework, do all that wonderful stuff. And since you're still listening right here, I appreciate you. Be a better person in the world today. Know that not everybody out there is that, but you can do your part to make life in this what can be an amazing, stressful, happy, sad, crazy world that we live in. Do your part to make sure that you are, what is it? I love this book. I don't know if you guys remember this book. Be a bucket filler. Be a bucket filler. If you don't know what I'm talking about, search some children's books and see what you get from that. We'll talk to you later. Mr. Bells is out.